In this video, I will cover the second iterative method to solve system of linear equation. In the previous case, we covered the explicit method, which presented by Jacobi, where your current iteration requires to get all the information totally from the previous step. But in this case, which is the more complicated method here, Gauss Seidel, Seidel, Gauss-Seidel, different pronunciation. But Gauss iteration method is implicit method, where you actually, for the current iteration, you mix data from the current and previous results. I will explain that. Let me first list the 5 equations that we got for the one-dimension heat conduction problem reported in the previous recording. So the equation were 20 minus 2t1 plus t2 equal 0. Then we have t1 minus 2t2 plus t3 equal 0. t2 minus 2 t3 plus t4 equal 0. Then t3 minus 2 t4 plus t5 equal 0. Then we have t4 minus 2 t5 plus 100 equal 0. Then before we do the Jacobi method, we did actually rearrange the equation to get t1, t2, t3, t4, t5 isolated to the left-hand side. You pick any equation. I like to move in an order, but this is what we did. You can check the Jacobi method recording portion. T1 is equal 0.5 t2 plus 10. T2 is equal 0.5 T1 plus 0.5 T3, and T3 is equal 0.5 T2 plus 0.5 T4, then T4 is equal 0.5 T3 plus 0.5 T5, and T5 is equal to 0.5 T4 plus 100. So what I did, I isolated T1 to the right-hand side. I kept everything else to the other side. So these are the equations. Now, if you like to use the Gauss-Seidel iteration method, which is implicit method, for example, we will get T1, right? We would like to get T1 here from the first step. So T1 at the current iteration, P1 plus P plus 1, will use T2 from the previous iteration, very similar to what we did with Jacobi method, right? But now when I move to the next equation, I need T1 and T3. So far, up to this limit, T3 was not calculated, right? So T3 will be taken from the previous step, correct? But T1, according to Jacobi method, we took that from the B iteration, from the previous one. But now the implicit method is using whatever is available from the current or previous. So T1 was calculated from the previous step. So I'll take T1 from here, substitute into this equation. So this T1 will from the current iteration. Now I will get T2, the new value, right? Let's move to the next step. I need T2 and T4. T4 never been calculated in the previous equations here, so this will be taken from the previous step. T2 is already calculated here, so I'm going to cross T2 and use that current value at the current iteration to calculate the new iteration for T3 at P plus 1. Now, you go further. T5 is mentioned for the first time. I will get it from the previous iteration step, but T3 is already calculated here, so this will be from P plus 1 to calculate T4 at the new iteration. Same T4 will be used to calculate T5 here, so that's P plus 1, and this is just a coefficient to calculate this one here. Now, you got new values for T1, T2, T3, T4, T5, then you would use that for the next iteration, and so on. This is how you use the, if the data is mentioned for the first time, you got from the previous iteration, but if the data is calculated at this current step, you're gonna use it for the current step as well for a new value here. So this is how it looks like. Let's build up the table like what we did with Jacobi method and see how things will look like. So I'm gonna draw a table here. I'm going to list T1, T2, T3, T4, and T5. And this is iteration 0. Okay, now I'm at the beginning right now, correct? So at the beginning, I will assume everything is 0 because I don't have anything. So for the first step here, I'm gonna put everything is 0, correct? 0, 0, 0, 0, 0. That's my first guess. Now let's move to the first iteration. Now, for the first equation, T2, I will take it from the previous one. So I will have T2 is equal 0. So that's 0.5 times 0 plus 10. So I'm going to end up having T1 is equal 10. Let's go for T2. To calculate T2, I need T3, which never been calculated before. I will pick it up from here. But T1 is now calculated at the current step. So if I want to get T2, the equation will be 0.5. Now, instead of taking T1 from here, I will take it from here. 10 plus 0.5, T3 is 0. So I'm going to end up having this equal 5. Now, T3. T3 requires T2 and T4. So T3 is going to be 0.5 times T2 plus 0.5 times T4. T4 never been calculated, still coming down there. So I'm going to take that from the original iteration 0. But now T2, it's already calculated in the current step. So I'm going to take that value of 5 to calculate this. So this will be 0.25. Let's do that in red like the other values. Is it? It's, sorry, it's 2.5. It's 2.5. Okay. Now let's move to T4. I need T3 and T5. So it's going to be 0.5 times T3 plus 0.5 times T5. T5, it's coming down, so it's going to be 0. That's the initial iteration. But T4 requires T3, and T3 was already calculated. So I'm going to put that 2.5. So this will give me actually 1.25. Then going for T5, I need T4. T4 already calculated, so I'm going to get 0.5 times 1.25 plus 100. You will get the value of T5. Now T5 is coming to be 50 times that's actually should be 50. That's 100 here, but this should be 50 because you divided by 2. So this should be 50 in here. Okay, so this would be 50.625. Okay, now let's see the second iteration, how it looks like. I'm in the second iteration now. Okay, let's get T1. T1, it requires T2. At this iteration, I didn't calculate T2 yet. So I will pick T2 from the previous step. So here will be 0.5 times 5 plus 10. So that's going to be 12.5. Now, let's go for T2 in iteration number 2. I need T1 and I need T3. At this iteration, T3 is not calculated. I'm going to take it from the previous one. So I'm going to have 0.5 plus 0.5. T3 will be taken from previous one. There's going to be 2.5. But T1 in this equation, it's already calculated at the current iteration. So I will take 12.5. Then you calculate that value, it's maybe come to be 7.5. Now, let's go for the T3. I need 0.5 times T2 plus 0.5 times T4. T4 is not calculated yet at this second iteration. I will take it from the first iteration to be 1.25. But now T2 is already calculated at the current iteration, so I will take 7.5. So we use whatever is available at this iteration, at the current iteration, then what's missing is taken from the previous one. So with this, you will end up having like 4.38. Now, next equation, I will have 0.5 times T3 plus 0.5 times T5. T5 does not exist in this current iteration, so this will be 50.625. And now I need T3 that's already calculated 4.38. You will get that value here to be what? 27.5. In the last equation, 0.5 T4 plus 50, and T4 is taken from this 27.5. So you end up having like 63.75, and you keep going until the difference between T1 value at iteration X and at the iteration X plus 1 is within the margin of the error that you are satisfied with, which is 0.01 or 0.1. The smaller the epsilon value, the longer the iteration will be. So if you fix the same 0.01 error or 0.1 error, then you compare between Jacobi and Gauss, you'll find that yourself, you will achieve that error quickly. You will reach the steady state solution very quickly. So if you do that, you will find that at step number 33, 34, 35, you almost get the same answer for the iteration 33, 34, 35. So I got 33.33. I got here 46.67. I got for this one 59.99, and I got this 73.33. Then I got this to be 86.67. Again, this is very close to the analytical solution. It's almost the same as Jacobi method, right? But at much less iteration. In Jacobi, we reached that level at iteration 65. Now we almost like halfway to get the same result. So Jacobi is taking longer time, but Gauss Seidel or Seidel iteration method, because it's implicit, it's using more data from the current results, from the updated results, that shrink down the number of iterations that you need to reach the same goal with the same error in your numerical solution. So that's conclude how to use implicit iterative method to solve system of linear equation.